Hi, good morning. We're back. This segment I'm gonna go through the IIAR slide deck. Good morning. We're back. For the presentation I was going to do in Orlando. So the first slide is there's a handful of slides from IIAR, and this is a beautiful scene that we are not experiencing. So I'm doing this from Fort Wayne, Indiana, but I'm hoping it's as meaningful as possible. So really, before we get started, really want to extend our prayers and thoughts for everyone that's been affected by the coronavirus, and all the healthcare professionals, and for those who are going to be affected in the future. We pray for minimal impact and for everyone's health and safety. So the IIAR allowed me to talk about really evaporator placement, and I kind of focused in on penthouse evaporators because many of the installations we're seeing, the designers are choosing penthouse enclosures for the evaporators, and we'll talk about why and how some of those decisions are made. But we want to try to get through the presentation, and here were the learning objectives for the IIAR. First, understand the principles of in-rack freezing, because once you understand how the system works and how the air is routed, it makes the rest of the refrigeration design and execution much more straightforward. The next component is we want to understand ideal evaporator placement within the room or within the area we're doing the freezing. And then lastly, how to prevent operational issues, whether it be building related or airflow conflicts. So we've got to be concerned with evaporator defrosting and operation, and there's just a lot of things we want to try to balance and minimize any problems with good planning. So the first thing we're going to talk about is in-rack freezing system operation. So most people are familiar with the principle of in-rack freezing, where and the departure from conventional freezing or conventional blast cell freezing, where in a conventional blast cell, the intent is to have a dedicated room with an evaporator located in the top of the room, with a deck below the evaporator, and then below the deck would be an array of drive-in or pushback or flow-through pallet positions. And the design intent there is to create an organized airflow pattern so that the air that's being discharged from the evaporators will flow down over and around the array of pallets and then return to the other side of the pallet arrangement up past the deck and return to the evaporator. Where in-rack freezing targets the airflow exclusively through the spacer area dividing the layers of products. The other alternative is if some products have holes in the boxes sufficient for induced draft through those holes, and spacers are not needed. But we're going to talk about kind of the fundamentals and talk about the airflow in the single deep arrangement. So in-rack freezing, like I said, is really based upon the ability to induce sufficient airflow exclusively through the spacer area of a pallet while located in a single deep arrangement. So that one sentence really encompasses much of the thought process in the development of quick freeze or in-rack freezing. So being able to target that airflow through the spacer area enables us to do a great job of liberating heat, especially from the innermost cases, where, back to our conventional blast cell, the cases on the innermost parts of the pallets tended to lag significantly in freeze performance. And then you have the other challenge where some pallets are in a really good pathway for the airflow while others are not. So you get a vast difference in freeze performance pallet to pallet based on where the pallet is. So, and then the other thing we want to talk about is the single deep racking arrangement. So the single deep racking arrangement is key to our ability to get great airflow, great velocity in the spacer area. It also provides for very low cost, very easy, very safe handling of the pallets. So those of us that have been around warehouses, it's pretty easy to see the difference in productivity, safety, and cost. Having operators drive several pallets deep into a multi-level drive-in racking arrangement versus having single deep pick rack. So it's much more efficient and much lower cost on the handling side. But let's look at the major in-rack freezing components and their function. So the first thing, and we mentioned a single deep or select rack, some people call it. The racking arrangement is really doing a couple things for us. Number one, it's providing the support for the pallet in the single deep arrangement, and also the racking provides the interface with the balance of the in-rack freeze components. So we're modifying a section of single deep pick rack with a plenum space between. So the next component is the direct drive axial fans. So at the top of the plenum, or in the QFM, it's on the back side of the plenum box, there's a direct drive axial fan. And when that fan runs, it reduces the pressure in the plenum behind the pallets, which induces flow through the pallets and ultimately exhausts vertically into the room. The next key component is the swing seal, and it's a pivoting panel that is affixed to the top of every pallet location and provides for varying pallet height, so it's automatic adjustment pallet height. The next thing we want to do, we want to help the forklift operators to place and retrieve the pallets. So we provide a guide and a stop in the QF Plus arrangement, so the operator can deliver the pallet to the center of the opening, and they can insert it all the way until it stops. So that pallet stop also provides for an air block. So if you can picture the opening, the 40-inch side of the pallet may be 5.5 inches tall, and there's a lot of open space between the runners. So when that pallet's all the way up against the opening, the pallet stop prevents air from going through that open part of the pallet on the back side. The next major component are the air blocking panels. So the intent of the freezing system is to provide the only pathway for the air to enter the plenum has to be through the spacer area. So we want every other potential entry point into the plenum to be blocked off when we use air blocking panels. And then lastly, there's an option to provide temperature and measurement devices that can provide feedback to a control system. So here's kind of a graphic of a in-rack freeze system, and it shows the major components. So again, we start with a structural steel racking, single deep pick rack with structural beams, and we provide pallet guides on the upper positions, and we provide floor guides at the floor positions. And then we have the swing gate at the top of each position, and notice there's an array of pallet heights here, and when the pallet is loaded, the top edge of the pallet engages up against the swing gate and pivots the gate. So all of the spacer areas are able to flow, but there's no pathway above the pallet on the shorter pallets to enter the plenum space. And then between the pallet positions and on the ends, we have to block off the space, so there's blocker panels. And then we're also able to deploy some pressure and temperature sensing devices. So there's some very sensitive airside pressure measurement devices that can measure pressure down into fractions of an inch of water. So those are typically utilized on these systems. And then you can also check both incoming, which would be room temperature, and then discharge air temperature, and provide data back to a control system. Here's where it gets interesting for the refrigeration designer and contractor. So when you consider we're going to be constructing this in-rack freezing system inside of a freezer. It can either be in a dedicated area, dedicated room, or it can be out in the general storage area of the freezer. But where this is installed, the system imposes a large and rather concentrated refrigeration load into that freezer space. So because of the amount of refrigeration capacity needed in that fairly small area, that has driven a lot of people to choose Penthouse evaporators to offset the loads. And it also helps eliminate potential airflow conflicts, in-room evaporator defrost issues, and then all the other advantages penthouses have over IL evaporators. So drain line routing, fan and evaporator coil maintenance, it all becomes much easier. But when you look at the concentration of load, where an in-rack freezing pallet position can impose loads up to up to 1.25 tons per pallet position. And then when you look at the ability for the in-rack freezing systems to go, follow the height of the building, we're able to have very high concentration of pallet positions in a very small footprint of the facility. So we're creating these very high concentrated loads, and the Penthouse evaporators really enable the refrigeration designer a lot of flexibility there. The next advantage is the ability to continue to run the in-rack freezing system while individual Penthouse evaporators are defrosting. So you may have 6 Penthouse evaporators in a freezing area, and you don't have to interrupt the freezing process happening in the in-rack freezing system to adequately defrost one of the penthouse evaporators. Another clear advantage for penthouse evaporators is they're inherently protected from material handling equipment or forklifts. So it's just amazing through my warehousing career how many things can possibly be hit and damaged inside of a warehouse. It's rather stunning. But getting the evaporators up and out of the room and into a penthouse really protects those units from the forklift operators. And then clearly, penthouse evaporators and fans are very easily accessed for maintenance. The in-room evaporators pose much more of a challenge, and with a penthouse evaporator, a good refrigeration technician will defrost that thing, warm up the box, and then go change a fan, where that's really not an option when you have aisle evaporators or in-room evaporators. So the next thing we kind of want to just talk about is the direct drive fans and the airflow through a conventional penthouse. Very straightforward, but when you start the fans, so in this example, our fans are discharging vertically downward. When the fans start, we're inducing airflow across the coil bundle. Notice the penthouse, they have blocking panels, so the only pathway for the air when the fans start is through the coil bundle, kind of akin to the quick freeze blocker panels. So obviously when we're inducing flow through the coil, we are pulling return air, shown as the red arrows, up into the return side of that penthouse. So that those return arrows are being pulled off of deck level from the freezer ceiling, and then we are discharging vertically downward. So now we're going to look at combining the airflow, the placement and airflow between the in-rack freezing system and our penthouse. So when you look at an installation of some quick freeze in-rack freezing, they're typically installed to where there's a narrow aisle or very narrow aisle, depending on the material handling equipment. So there's a drive aisle between the sections. So this is a very typical installation, and you can see the fans are discharging vertically up. So you can really look at, on the left-hand side of the graphic, an in-rack freezing system is really an array of air inlets, floor to top, and then a handful of air outlets from the shared plenum space. So now let's locate that penthouse evaporator, and the ideal placement provides for a vertical down airflow arrangement from the penthouse. So we have all of these air inlets in this array of in-rack freezing, and then we have the air outlet, or the discharge air from the in-rack freezing, vertical up toward the deck. But we are putting the discharge air from the penthouse, which is the lowest temperature air, down into the aisleway, where each individual pallet position will then induce flow through the product and then back up through. So I think it's pretty apparent when you look at the graphics why there's a desire to get the vertical down into the in-rack freezing aisle, and allowing the return air to be pulled from deck level. So one thing we're going to want to avoid is airflow directly into the return air pathway of the penthouse. So clearly we want to avoid interrupting the defrost of the penthouse evaporator. So we will definitely want to avoid discharging air directly into the return. But most of the aisle arrangements will avoid that return. So it depends on the dimensions of the penthouse and the exact location of the discharge coming from the in-rack freezing fans. Here's another view. So this is like from the floor looking upward. The ability to, this gives you a little better perspective to see the distance between the discharge of the fan and the inlet of the penthouse evaporator. But clearly a good design can prevent the conflict of blowing in-rack freezing air up into a penthouse, which would complicate the defrost of that unit. So with the vertical down arrangement, one thing we really want to help is to maximize the performance of the penthouse evaporator. We're going to want to plan to get the penthouse located properly. So we talked about how it's best to get the fans vertical down into the center of the aisle while avoiding the return. But we're also going to want to look at how we can plan with the building designer and with all the placement of any trade putting utilities in the room. So short circuiting of a penthouse happens if there's either inadequate natural separation between the discharge airstream and the return airstream, or there can be obstructions. So if there was good separation between the discharge and the return on the penthouse, but you obstruct the outlet area of the fans, that can cause a short circuiting. So it can, like if you're blowing down on conduit or sprinkler lines, that can definitely reduce the effectiveness of the penthouse evaporator performance, and it can complicate service. So what we want to encourage people to do is, number one, plan with the steel designer to provide optimum joist spacing in the penthouse area. And it's pretty straightforward. The ideal joist spacing in the penthouse area equals the fan center distance. So if we're getting that space between the joists, or the joist spacing to match the center distance of the fans, there's going to be space for great space for airflow coming down there, and it'll be unobstructed by joists and reinforcements and the rest of the structural steel. The next thing we want to do is make sure there's good documentation on the plans and good communication and follow-up with all the contractors that will be working especially in those aisleways. So it's going to take planning and work with the electrical designer, the fire protection, and anyone that is routing any communication. There might be wireless access points, and other equipment that we want to be placed in areas away from those critical penthouse areas. So clearly we want to work with people to make sure that there's good documentation on the drawings, and again, follow up. Because if you're the electrician or the sprinkler contractor and you're going to be on a scissor lift and you're running utilities, the easiest place to run them is in the center of the aisle. And that's really the worst place for us. But as long as it's known, it's documented, and it's followed up, it's pretty straightforward to plan around there. So we're going to show an example of marking a drawing where we're calling out no conduit runs, no sprinkler mains, and it's really best to ask for no joist cross bracing in the fan area. We're going to want to bring a duct extension into that area, which we show in a future fan. So when you're working with your penthouse supplier, we're going to ask for fan housing extensions, so we're able to route that discharge air down near the bottom of the joist. That really helps provide that separation that the penthouse really needs to divide the discharge air from the return air, so we don't get that short circuiting, and we do get that direct velocity down the center of the aisle toward the floor. So this shows the ideal joist space equaling the fan center distance. So depending on the evaporator you choose, you can look at their standard fan spacing, and you may have a match, or you may have to work with the steel designer to accommodate that center distance. It really helps a quality installation and performance and future service. So there's notes you can put on your drawing in plan view to show avoidance areas for other utilities. You certainly wouldn't want a lighting fixture blowing around in the discharge of a penthouse fan. But let's also get the sprinkler mains, conduit runs, joist spacing, all of that is as clear as possible so we get maximum benefit from our penthouse evaporator. Another thing we want to talk about is the fan discharge extension. This is kind of akin to a long throw adapter on an aisle evaporator, but it provides additional separation from the discharge airstream from the return. So we have return air coming over here, and it's lower velocity than the discharge from our fans, but we want to keep these airstreams as separate as possible to get maximum utilization of our penthouse evaporator. So this because we specified the correct joist space and no obstructions, it enables us to get this fan discharge extension in there and provide better separation and better throw toward the floor. Some other considerations: some early in-rack freezing designs utilize a centrifugal fan design with a horizontal or radial air discharge. These systems pose a different set of airflow challenges for all evaporator types. And then there's just a few notes. If you encounter one of these horizontal discharge systems, it's best to provide a longer fan extension housing to extend past the horizontal discharge area. The next slide shows the kind of the airflow pattern of one of the horizontal discharge systems. And then the other recommendation is to interrupt fan operation with aisle evaporators. So when you consider these fans sit on top of the plenum, on top of the in-rack freezing system, and there's a motor, belt-driven pulley system with a shaft and bearings in this arrangement. And when the fans are running, they are discharging outward radially, 360 degrees. So it's important to get the evaporator air down below that discharge area, so we're not mixing those air streams on the way down toward the center of the aisle. You can also see the challenge if you had used in-room evaporators. They're operating at the level somewhat near the same height as these fans that are discharging air radially. So they historically have caused some defrost challenges with in-room evaporators. So there's typically not an operational challenge with penthouse evaporators that have a discharge duct that routes the air all the way down past that level. So that's the last slide in my slide deck. I was going to open this up to questions, but I think it's pretty straightforward. There's again the challenge really is rooted in the large capacity required in a fairly small area. It really makes the refrigeration designer and contractor's job a little more challenging, and if things aren't executed well, it can really cause problems. So I encourage everyone to number one, understand the load concentration and the challenges associated with evaporator selection, placement, operation, defrost, maintenance. Just make sure all those things are considered when you're doing your design, and you'll end up with a great solution. So thank you everyone for jumping in and allowing me to share this presentation. Sadly, I wasn't able to do it in sunny Florida, but I hope to see everyone, all of our friends and contacts in the industry as soon as possible. Thank you so much. Take care.